we have Subrata as a review speaker, and I'll invite Professor Sushanta Datta to introduce the speaker and coordinate the session.
Well, good morning. It's a great pleasure to introduce Subrata, whom I had met many years ago. So I had actually forgotten whether he was Mukherjee or Mukhopadhyay. That could be an issue with SIR, I suppose. So Subrata, when I met him first, the Princeton University. Later on, he was postdoc at Berkeley, and since then, he has been in the faculty of Indian Institute of Science, Bangalore. He is a pan-Indian man, as I learned yesterday. He grew up partly in Delhi and partly in Hyderabad, studied in St. Stephen's College in Delhi, and now he is in Bangalore. He has worked in many different areas of condensed matter physics, and we're looking forward to his talk.
Thank you very much, Sushanta, for that very kind introduction. And I'd also like to thank the organizers, especially Satyavrat and Brijesh, for putting together this amazing conference and inviting me to speak in it, give this review talk. It's a real honor for me to do so, and I'm very happy to be here. So I'm going to be talking about, as the title suggests, thermalization in quantum many-body systems, and more importantly, the lack of thermalization. Situations in which this many-body system does not generically, perhaps, reach a state of thermal equilibrium, a phenomenon that's called many-body localization. So before I begin, let me start with a few disclaimers. So first of all, this is not a talk for experts on many-body localization, and there are several of them, I guess, at this meeting. There have been sessions on many-body localization. So if you are an expert, then you're not going to get very much out of this talk. You're not going to learn something which you don't already know. So this is really directed towards non-experts and especially students. So that's the first disclaimer. The second is that this is a field in which there's been a lot of activity over the last 2 decades, a lot of different calculations, some number of experimental results. And it's certainly not possible for me to give a review of all of that in the limited time that I have. And so I've only really selected just an infinitesimal fraction from among those results to convey the message that I would like to convey. And based, of course, on my own discretion and my own biases, I'd like to believe that the results and the calculations that I've left out would not significantly alter what I have to say. So that's another disclaimer. And the third one is that I'm going to try to keep the talk more at a conceptual level than worry too much about technical details. So every now and then I'm going to be a little glib in my language, with due apologies to the experts in the field, and I hope that you won't mind that glibness. Okay. So with that, let me just tell you what the outline of my talk is going to be. So I'll first tell you about what we currently know and understand in terms of how thermalization takes place in quantum many-body systems. And then I'm going to introduce this phenomenon, many-body localization, as the antithesis of that, meaning as a phenomenon which has to do with the absence of thermalization. I'll tell you about the phenomenology of this particular phenomenon, and we'll describe a phenomenological model which seems to work reasonably well. And then I'll show you a few numerical and experimental results and discuss their implications, especially for the existence of this phenomenon, because the phenomenology sort of takes it for granted that the phenomenon exists, but there are issues that show up when you look at the numerical and experimental data which sort of question that. So I will discuss that, and then finally I'll talk about one particular mechanism that has to do with this transition from the many-body localized phase to a regular thermal phase and its implications for the stability of many-body localization. Okay, so that's going to be the plan. So let's just start with something that most people here are probably familiar with, the standard setting of statistical mechanics for isolated classical systems. So this word isolated is very important here. So the systems that I'll be considering, whether they're classical or quantum, will be assumed to be isolated and not in contact with the heat path. So if you're looking at isolated classical systems, the standard textbook setting is that you usually consider a gas of n particles in a box, and the box doesn't allow any exchange of particles or energy. And so you can, of course, in principle, have a microscopic description of the system in terms of trajectories of these particles in 6n dimensional phase space. N is the number of particles, and I'm assuming that this is in 3 dimensions. So you have a 6n dimensional phase space, and you can in principle track the trajectory starting from some initial condition, and any point in this phase space in principle gives you all the information at that instant of time that you need to know about the system. And so the approach towards an equilibrium macro state, starting from some particular micro state of the system, some particular initial condition of these particles, can be thought of in terms of dynamics in this phase space, and of course it depends on the interactions between the particles. And so you can ask, well, what is required for the system to thermalize, to reach a state of macroscopic thermal equilibrium described by only a handful of macroscopic parameters? And so in the classical case, one of the things which you of course need is that the particles have to move in the absence of interactions. They have some momentum or some kinetic energy, so they move. Then you very crucially need interactions between the particles. So energy, momentum, etc. can be exchanged between them in the approach to equilibrium. And it's important that the dynamics be such that you get some chaotic trajectories in phase space. And this chaos is required to wash out any memory of the initial conditions, and also basically to, in some sense, for the system to rapidly in quotes, approach thermal equilibrium. So you need these conditions. And it turns out that these conditions give rise to diffusion and transport of conserved quantities, which are of course required for thermalization. Now, this is generically true for any classical system. These conditions are generically met for classical systems. Of course, there are special systems for which these conditions are not met. For example, integrable systems in which you have a very large number of constants of motion which constrain the dynamics. But those systems are special, and typically those constraints go away when you perturb them slightly. So this integrability is not a robust phenomenon. So even though integrability is something which doesn't allow thermalization, it's not a robust phenomenon. It disappears when you perturb. Okay. So that's all I have to say about classical systems. Now you can ask, well, what about quantum systems? How does one look at thermalization of quantum systems? And so if you try to think of it in classical terms, there are problems which arise. So one problem, of course, is that there's no really well-defined phase space for a quantum system of particles because of the uncertainty principle. You can't specify the momentum and the position of a particle exactly at any instant of time. So there's no well-defined phase space in that sense. And so you also can't think of microstates in the classical sense. But it turns out that the equivalent of a microstate for the quantum system is actually the state ket of the system. So that is like the microstate. And the Hilbert space in which the state ket exists and evolves plays the role of the phase space. Okay. And so if you have a closed system, and I'm assuming that there's a time-independent Hamiltonian which describes it, then you know that the state ket satisfies the Schrödinger equation. And so this is what gives you the evolution of the state ket. Now the point is that since this is unitary evolution, in this kind of evolution, as far as the state ket is concerned, there really is no notion of chaos. There's no notion of diverging trajectories, because the unitary evolution in this Hilbert space will actually conserve distances and angles. So this evolution will not give you any notion of chaos like for the classical system. So if there has to be some notion of chaos in this quantum system for it to be able to thermalize, it has to be elsewhere. And so where else could it be? So it turns out that if you write down the evolution of this state ket, the evolution depends on the energy eigenstates of the system and the energy eigenvalues. So any state ket is going to evolve in this way, as you know. And so if there's a notion of chaos which exists, it somehow has to lie in the energy eigenstates and in the energy eigenvalues and in the energy eigenstates. So these objects somehow have to encode in them some notion of chaos. And so this is something which was realized quite early on, and now is something that we understand pretty well. So it turns out that as far as the energy eigenvalue spectrum is concerned, for a quantum system which thermalizes, these have spectral properties similar to those of eigenvalues from random matrices. And the thinking behind this is that if the system thermalizes, then basically, it doesn't have an extensive number of conservation laws. It at best has a handful of conservation laws. And once you have accounted for them and block diagonalized your Hamiltonian taking them into account, then each block doesn't have any particular structure. It looks like a random matrix. And so you would expect the eigenvalues to look like the eigenvalues of a random matrix. And it turns out further that because of that, there's more information that's contained in what's called the level spacing distribution. So you arrange the eigenvalues in some ascending order or descending order of magnitude and look at the difference in energy between successive eigenvalues normalized by the mean value of the spacing. And the distribution of that is something which actually encodes in it this particular property of the eigenvalues. And so when you have systems which thermalize, which have eigenvalues like those which arise from a random matrix, this level spacing distribution has this particular form, P of S. And what's important is that S P of S goes to 0 as S goes to 0, which is the concept of level repulsion, which tells you that because there are no extensive number of conservation laws, once you've accounted for the other ones, there are no degeneracies left. And so your level spacing distribution goes to 0 as S goes to 0. On the other hand, if you have an integrable system, something which doesn't thermalize, then its level spacing distribution actually has a Poissonian structure like this. So there's no level repulsion. So this is as far as the eigenvalue spectrum is concerned. If you look at the eigenstates themselves, then it turns out that the eigenstates also encode in them some notion of chaos. Now, where does that come from? So that comes from the following argument, that unlike in a classical system, in a quantum system, you will always have a set of states which don't evolve under Hamiltonian evolution. And these are the energy eigenstates. You know that they don't evolve, they're stationary states. And so if you now say that the system has to thermalize regardless of what the initial state was, right? That it has to reach a state of thermal equilibrium, then if the initial state was an energy eigenstate which doesn't even evolve, the only way in which this can happen is if somehow that individual energy eigenstate was like a thermal ensemble itself. So that is sort of, it's a pretty profound realization. But this is the essential principle of what's called the eigenstate thermalization hypothesis for a quantum system, that the energy eigenstates themselves are like thermal ensembles, are like thermodynamic ensembles. And so then the picture of thermalization is something like this, that you have individual energy eigenstates, which by themselves are thermodynamic ensembles. But then you can take some linear superposition of these to get an arbitrary state, and that arbitrary state will not look like a thermal ensemble by itself, but then as it evolves, the phase relation between that existed at time t equal to 0 between the energy eigenstates and the superposition gets scrambled. And so after a sufficiently long time, in sort of the infinite time limit and also in the thermodynamic limit, the phases get completely scrambled. And what you have then is just a decoherent mixture of the energy eigenstates. And each individual energy eigenstate was like a thermodynamic ensemble. So this whole thing evolves into a thermodynamic ensemble. And so this is one of the statements of thermalization in a quantum system, that if you look at the expectation value of some physical observable as a function of time, then in the limit of infinite time and in the thermodynamic limit, this tends to some microcanonical value with the microcanonical density matrix consistent with what the energy of the initial state was. Okay, so this is the basic idea of eigenstate thermalization. And there is a more precise mathematical statement for the matrix elements of these operators, which gives you sort of the mathematical structure of the eigenstate thermalization hypothesis. So the mathematical structure is not very important, except for the fact that if you look at the expectation values in eigenstates, then it turns out that the expectation values of these physical observables in energy eigenstates of the function of energy is some smooth function. And then you have some fluctuations about this, which are encoded by this part of this formula. But these fluctuations fall off exponentially in the size of the system, because there is the entropy of the system sitting in the exponential, which is extensive. So you have fluctuations in the expectation values of these observables, and the off-diagonal matrix elements are also exponentially small in the system size, and it turns out that that's required for the system to reach thermal equilibrium in some reasonable amount of time. And I'm not going to go into the definition of what reasonable means in this particular case. Okay, so as far as thermalization of isolated quantum systems is concerned, it turns out that this is sort of, what we believe is required for isolated quantum systems to thermalize, that the energy level spacing statistics is random matrix-like with level repulsion, and you have transport in the system. Things, conserved densities should be able to distribute, and so you have non-zero conductivities and diffusive transport. The eigenstate thermalization holds, and then there are some other things which have to do with entanglement and also how subsystems thermalize, which I won't go into. But these are all characteristics of thermalization in isolated quantum systems, and together sort of give you a complete picture of how that happens. Okay, and so all of this was just sort of theorizing, but it turns out that you can also, this has been numerically verified, and so this was one of the first numerical calculations that was done on some very generic quantum interacting system in which the statistics of these matrix elements was obtained numerically. And as you can see from here, okay, it may not be very obvious from this plot, that what you have is you actually have something which is a pretty smooth function of the energies of these eigenstates, the expectation values, and you also have fluctuations which are, pretty small and exponentially small in the system size. Experimentally, isolated quantum systems are difficult to actually synthesize. Your best bet is to do it in cold atomic systems. So this is an experiment that was performed in a cold atomic system in which the system was started out in a pure quantum state and evolved. And this pure quantum state was such that the occupancy of particles in this optical lattice was not something that would correspond to thermal equilibrium. And as the system was evolved at different energies, and the temperature here is a proxy for energies, it turns out that you end up within the time scale of the experiment getting distributions which look thermal. Okay, so this is, so basically in a nutshell, what I've said so far, that with quantum thermalization, you basically have some single particle states, right? And then you need interactions. Like I said, in the classical case, even in the quantum case, you absolutely need interactions in order to thermalize. And so the picture is that in the absence of interactions, you have some single particle states which are capable of supporting transport. And then you turn on interactions, and then you get thermalization in the system. Now, this is certainly true for classical systems. As I said, the classical systems, no matter what you do generically in the absence of interactions, will have some mobile single particle states. But the situation is actually quite different quantum mechanically. So quantum mechanically, it turns out that in the absence of interactions, if you're looking at single particle states, unlike their classical counterparts, you can actually have a situation in which you have single particle states which support no transport. And these are what are called localized states. And so this can happen generically, and it can also happen for the entire spectrum of single particle states. So now you have this question. So suppose you have these single particle states which are incapable of supporting transport, and then you turn on interactions. Will the system thermalize or will it not? Because it appears that one of the necessary conditions, that things be able to move, is not satisfied. But on the other hand, you are turning on interactions, so what happens? Okay. So first of all, how do you get these immobile states in a quantum system? So this is basically the phenomenon of localization, which was discovered by Phil Anderson many, many years ago. And an essential ingredient for that is to have either disorder, some random potential in which these particles move, or to have a quasi-periodic potential, a non-repeating potential, deterministic but non-repeating potential in which these particles move. And it turns out that the reason that you have this phenomenon of localization is that this is quantum mechanics. These particles are really waves. They're described by a wave function. And so you have some interference of these waves as they propagate through this irregular medium. And that gives you finally energy eigenstates of these single particles which are localized, which are not extended, which don't have any current. And it turns out that in 1 and 2 dimensions, all such states are localized in the presence of disorder. With quasi-periodicity, it's a little different, and I won't get into that in detail. But in 3 dimensions, all states are localized only for a sufficient amount of disorder Otherwise, you have a combination of extended and disordered states. But the important thing is in 1 and 2D, and especially in 1D, you will have a spectrum in which all your single particle states are immobile. Okay. So imagine that you have a situation like that, and now you're populating these single particle states with particles. And let's say these particles are fermions, so they obey the Pauli exclusion principle, and so you're populating them. And so now you get a many-body state of this non-interacting system. And so if all your single particle states were localized, then really your many-body energy eigenstate will also be localized. That will also not be capable of supporting any transport. So this is the simplest example of many-body localization. You have a many-body system in which all the many-body energy eigenstates do not support any transport. So there's no motion. Right. But this is, of course, very pathological because we were completely ignoring the interactions between the particles. And so the question is, what would happen if we turn on interactions? Even in the classical case, we know that even though the single particle states are mobile, without interactions, you don't have any thermalization. So what happens here? So you might on the one hand think that, oh, there won't be any thermalization because all the single particle states were localized. So how can anything move when you turn on interactions? But it turns out that there is a way in which you can still have motion. So even at the level of one particle, right, not the many-body state, when you have these localized states, there is a way in which the particles can actually tunnel between these localized states, provided they couple to some other degree of freedom, which in a typical solid state system with disorder happens to be phonons. And this is what's called variable range hopping. And this was discovered by Neville Mott, again, sorry, this year is wrong. This should be 1969 and not 2019, many years ago. And so this actually does allow transport at the single particle level in a completely disordered localized system. So now when you're looking at a many-body system, you have a similar notion of these localized many-body states, but now in sort of the many-body configuration space, Hilbert space or Fock space or whatever you want to call it. And so the question is, can you actually have this kind of tunneling in this Fock space for these many-body states? And there it turns out that unlike in this case where you need some external degree of freedom for the system, for the particles to couple to, here in principle just having an interaction between the particles can give you this kind of matrix element for tunneling. But the question is, even if it does give you that matrix element, will it actually give you the proper amount of tunneling that's required for transport to take place and for thermalization to occur? So this is really the question, the central question in many-body localization. That when you turn on interactions in this localized system, will you get transport or will you not? And if you do get transport, the system will eventually thermalize. And so there were a lot of, there's a lot of work, as I said, there's already been a lot of work that's been done, but in what I would call the first generation of results, it appeared that this would indeed be the case. And so there were perturbative arguments to say that this kind of many-body localization was stable against the introduction of interactions, meaning that interactions would not induce transport. And then the stability was also understood in terms of things called local integrals of motion, which I will come to. Okay. There's also a mathematical proof of the stability of MBL that was given, which has come under quite a bit of scrutiny in recent times, but I won't spend any time describing this. And importantly, there seemed to be strong numerical evidence for the existence and stability of MBL in 1D, in one dimension. And there were also experimental observations of lack of thermalization in these systems in an optical lattice, which seem to support this notion. Now, I say that these are first generation results. I should add that as far as the chronology of MBL is concerned, it's probably good to divide it into two phases, pre-COVID and post-COVID. I'm not suggesting that MBL had anything to do with COVID, at least as far as I know, right? But so these are all sort of these first generation results, which sort of essentially conveyed quite a bit of optimism as far as the existence of MBL was concerned. So let's just look at what these are. So again, I'm not going to do this in any amount of detail. So this is a table from a recent review article, which compares and contrasts the behavior of many different diagnostics for an MBL system and for a system which actually thermalizes. And these diagnostics have to do with looking at energy level spacing statistics, looking at other dynamical quantities that you can get from the energy spectrum, various kinds of entropies, density correlation functions, conductivities, and so on. And we don't need to go over all of this in detail. The only thing to sort of see is that generally what happens is that when you're in the MBL phase, things slow down. So for instance, something like the entanglement entropy, which increases linearly with time in the ergodic or the thermal phase, now increases only logarithmically in time. Something which is, we call the number entropy, which has to do with particle number fluctuations, which increases logarithmically in time in the ergodic phase, now doesn't even change as a function of time. So basically, this kind of localization is associated with transport being arrested, and as a result, things evolving slowly. Okay, so fine. So now, how does one look at all of this in terms of some concrete microscopic model? And so this is the model which has come to be known as the standard model of MBL. So it's a one-dimensional model, and one-dimensional because MBL, I think, is believed not to exist in greater than 2 dimensions, and greater than 1 dimension. This should be d greater than or equal to 2. I'm sorry, and this is something which almost everyone agrees on, and I'll get back to this. And so you look at this one-dimensional model, and so this is a simple one-dimensional model of fermions on a lattice with disorder and with interactions, and these are spinless fermions, so the interactions are nearest neighbor interactions, and the hopping is also usually just taken to be nearest neighbor hopping, and this is where the disorder sits. Okay, and you can also express this in terms of spin half degrees of freedom instead of these fermions, spinless fermions, through something called a Jordan-Wegener transformation, which people here are probably familiar with, and then the model looks like this, with the disorder sitting in this random Zeeman field at every term, and the interaction sitting in the ZZ coupling, and the hopping here is a coupling between the X and the Y components of the spins. So this is something that's been come to be known as the standard model of MBL, and it has been studied quite extensively numerically. Now the most reliable numerical technique that we have is numerical exact diagonalization. And the reason is that thermalization or lack thereof is really a question about what happens at arbitrary energies, not just at some low energy. So in order to answer this question, you really need access to the full energy spectrum of the system. And the only reliable method that we have to do that for generic interacting systems is numerical exact diagonalization. Now that of course comes with its own problem because you're limited to fairly small system sizes, typically about 22 sites for a model like this, can be pushed a little bit, but not significantly. And it turns out that, of course, if you try to go beyond brute force numerical exact diagonalization by using something more sophisticated like matrix product states, then you can go to much higher L, but it turns out that then there are limits on entanglement and time of the states that you can actually simulate. And so again, even this has its own limits. And so you're sort of confined to using numerics, but because of the nature of the numerics, you can't really go to very large system sizes or very long times. Okay. So there was a phenomenological model that was developed for the MBL phase. So this now assumes that MBL exists, and the question is, okay, let's say that MBL exists. What is the best way to understand what this MBL phase is? And so the idea is that you start with the standard model of MBL. And so if you didn't have any J parallel here, which is equivalent to not having any hopping in the corresponding particle model, and you just had this, then this is sort of trivially many-body localized because it has an extensive number of integrals of motion, all of these SZs, which commute with the Hamiltonian. And because, as I said, this is like the hopping and you've turned it to 0, there is no transport in this model. So this is trivially many-body localized. And so the phenomenological model of MBL, which you write down even when this term is not equal to 0, says that if the MBL phase exists, then the Hamiltonian for that, an effective Hamiltonian for that, is sort of connected to a Hamiltonian for this, meaning that it also has the same form. It's something which can be expressed in terms of Z components of appropriate spin operators, except that it doesn't have to look like this. It can have higher order spin coupling terms, like coupling 3 spins, 4 spins, and so on. But all of these are some kind of spin operators, Z component of spin operators, which commute with one another. And the Hamiltonian can be written down like this, and so you can see that each one of them now commutes with the Hamiltonian. So you again have an infinity of these integrals of motion. But these objects are not the same as those objects. In fact, these are dressed versions of those objects. So you can get these tau z's from the SZs by also adding these further neighbor terms and involving these strings of spin operators on other sites. But the important thing is that these coefficients are assumed to fall off exponentially with distance. The distance is involved here. And similarly, these couplings, which go beyond just one site, are also assumed to fall off exponentially with distance, the distance as described by these labels. So this is something which is a phenomenological model for the MBL phase. And these taus are what are called the local integrals of motion, or LEOMs, sometimes also called L-bits. And it turns out that this model is remarkably successful in terms of describing a lot of the phenomenology of the MBL phase, that there is no transport, that you have eigenstates with area law entanglement, and that you have some logarithmic spreading of the entanglement with time. Some of the things which I showed you in the earlier table. So those can actually be reproduced from this phenomenological model. So everything looks nice. Okay. So what about numerical results now? So I'm just showing you some select numerical results. So this one, for instance, and these are all on models like the standard model of MBL or similar models. So if you look at energy level spacing statistics, which I told you would be random matrix like if the system thermalizes, and Poisson like if it's in the MBL phase, because you have all of these this extensive number of conserved operators. So this is a single number that you can get from the level spacing distribution. It's called the ratio of successive gaps. We don't need to go into what it is, but it turns out that it has a certain value if you are in the thermal phase, and a certain other value if you have Poissonian level spacing statistics in the MBL phase. And so in the standard model of MBL, as you increase the disorder strength, you actually see for different system sizes this number going from its thermal value to its MBL value. So it looks like you have these two phases and you have a transition in between. But I will come back to this plot and look at it in more detail in just a couple of slides. Similarly, if you look at the entanglement entropy of the energy eigenstates, in the thermal phase, this is supposed to be a volume law. And in the MBL phase, this is supposed to be an area law. And indeed, you see something like that happening as you vary the strength of disorder. In this particular case, that's represented by H and not by W. So at small values of the disorder, you're in the thermal phase, you have a volume law. And at smaller values, you have an area law. Then calculations have also been done, dynamical calculations, to see how the entanglement entropy increases as a function of time, starting from an unentangled state. And in the MBL phase, the prediction is that it goes as log t. And indeed, that's also been seen in these numerics. And this is sort of, it's not very clear from the way that I presented it, but this is a quantity which tells you whether the ETH holds or not. And it turns out that you can actually reduce it to one single quantity and look at its scaling with system size. And if this quantity increases as a function of system size, then ETH holds. And on the other hand, if it doesn't, then ETH does not hold. And once again, as a function of increasing disorder, you see ETH doesn't hold. And so this again is an indicator that you have a thermal phase and an MBL phase. You can go from one to the other as you increase disorder. And so all of this can be summarized in terms of a phase diagram, where this is the energy of the eigenvalues, this is the strength of disorder. And so you have some thermal phase. So everything here is delocalized in thermal, all the energy eigenstates obey the ETH. And here you have the MBL phase, and you can go from one to the other by changing H. So you have some kind of a transition. And the phase boundary here is not really a straight vertical line, it's actually curved. So this corresponds to what's called a many-body mobility edge, but I'm not going to go into details of that as well. And so different diagnostics can give you slightly different phase diagrams, but for the standard model of MBL, which I showed you, these kinds of numerics give you a value of H at which this transition seems to take place at about 3.5. Okay, and so then there are also experimental observations on systems of cold atoms, in which the basic idea is that you take this isolated system of cold atoms, you started out in some initial state in which the distribution of something is very far from being thermal. In this experiment, that's basically on an optical lattice. That's basically the density distribution of particles on the optical lattice. So you start from a far from thermal distribution. You let the system evolve, and you ask whether the system thermalizes or not for different amounts of disorder. And indeed, for up to the lifetimes of these cold atoms experiments, it appears that for the right amount of disorder, if you have sufficiently strong disorder, then the system does not thermalize, because thermalization in this experiment would mean that as a function of time, everything should just go to zero, and it doesn't. And in a similar experiment with trapped ions, again, you see the same thing happening, that something which should go to zero if the system thermalizes does not actually go to zero even after long times when you have a sufficiently strong amount of disorder. Okay, so let me just give you a quick aside on quasi-periodic systems. I'm really not talking about my work here, but it turns out that even in quasi-periodic systems of a certain type, in which you can actually in 1D have coexisting single particle localized and delocalized states, there is perhaps a notion of non-ergodicity, some kind of athermal behavior, which is different from conventional MBL, because it has subdiffusive transport as opposed to completely arrested transport. But you can actually have such kind of non-ergodic phases, possibly. And this is something which has come to be known as a non-ergodic extended phase. Okay, so anyway, so this was basically the summary of these first generation results. I have about 10 minutes. So in the remaining 10 minutes, let me just now start poking holes into everything that I told you up to this point. Okay. So this is sort of the summary of first generation results, that you can do numerical exact diagonalization. This is the most reliable technique, and within sort of the limitations of that technique, through various diagnostics, it appears that you have a thermal phase, you have an MBL phase, and there's a transition between them. And then there's also experimental observations which suggest the lack of thermalization interpreted as MBL in systems of cold atoms. And there's also a phenomenological model which has been developed based on these local integrals of motion, which seems to account pretty well for whatever you would expect to be happening in the MBL phase. So all this seems very nice, but, okay, so what was the but now? Where's the problem? So the first hint of the fact that there could be a problem comes from trying to understand this transition between the thermal phase and the MBL phase. Okay, so how do you try to understand this transition? Now, for single particle localization, in 3 dimensions, as I told you, right? You can have both localized and delocalized phases, single particle states, and for a sufficient strength of the interaction, of the disorder, you can localize all states. So you can actually have a transition in the non-interacting system between a phase which is localized in 3D and a phase which is not localized. And so this is called the Anderson transition. And so it turns out that this transition can actually be described in terms of single parameter scaling. There is just one single length scale which diverges as a function of the parameter that you're tuning, which is the disorder strength, with a certain critical exponent. And so this is, this seminal piece of work was done, again, several decades ago by Anderson, Abrams, Licciardello, and Ramakrishnan, who came to be known as the Gang of Four. And so anyway, I'm not going to again go into the details of what this plot exactly means. So suffice to say that this particular object, which is called a beta function, if it goes through zero as a function of the parameter that's being tuned, you can think of that as the disorder strength. If it goes through zero, then you have a transition. And that happens only in 3 dimensions. And in 1 and 2 dimensions, it doesn't go through zero. And that tells you that you only have a localized phase, but here you do have a transition. And fairly recently, what we've seen is that something similar also happens in an appropriate kind of quasi-periodic system in 3D, that you again have this transition. And these are all, and what you see is actually consistent with this, having a single diverging correlation length with a correlation length exponent nu. Okay, and that can be calculated. Now here's the thing. So it turns out that you're looking at this correlation length exponent nu in a system with disorder, or what's called quenched disorder, which is certainly true for these systems. Then there's a certain bound on this exponent. So this exponent has to be greater than 2 divided by the number of dimensions that you're in. So for the 3D Anderson transition, you can get this exponent numerically, and it does satisfy this bound. But if you try to do the same thing for MBL, for the MBL transition, if you try to think of it in terms of single parameter scaling and try to extract this exponent from that single parameter scaling, then you get a nu which is very close to 1, and d for the MBL models is 1. You're in 1 dimension. So this strongly violates this bound. And so the question is what's going on now, right? Like you would expect that this bound would hold if there's a true transition, but then when you try to extract nu from numerics, then this bound seems to be violated. And so this could point to various things. So maybe there's no single parameter scaling. Maybe your system sizes are not large enough for you to actually be in the proper scaling limit to get this. Or more drastically, maybe there just isn't a phase transition. And then there's also, a notion that perhaps this particular bound does not really apply to quantities that you obtain from many-body diagnostics, that even within sort of the MBL scenario, this is really something which should apply only to quantities that you can get from single particle, quantities related to single particle physics. But whatever it is, so there's a problem. Then the other problem is that, so this is the plot that I showed you earlier, in which this particular number went from having its value in the thermal phase to the MBL phase, and I said, oh, you see it goes from here to here, and there seems to be a transition. But if you try to ask where the transition is, right? So if you had a sharp phase transition described by single parameter scaling, what you would expect is that all of these curves would actually, for different system sizes, would intersect at the point at which you have this transition. And here you can see you don't see that, right? These curves for different system sizes actually don't intersect at one point. And in fact, if you try to extract an intersection point from these curves, then that intersection point drifts as the size of the system increases. So for instance, L equal to 8 and L equal to 10 intersect somewhere there, and L equal to 20 and L equal to 22 intersect somewhere there. And so there seems to be a drift in the value of disorder strength required to get to the MBL phase as you're increasing the system size. And the point is that if this drift continues indefinitely, right, and so your critical disorder strength actually goes to infinity as L goes to infinity, there is no MBL phase then. Everything is thermal. And it also turns out that when you try to scale this using single parameter scaling, then, so I have 5 more minutes, right? So I was timing myself. So can I take 2 or 3 more minutes after that?
Well, for the system
collapse.
And
right, exactly, right. So there's been system collapse, but there's probably no data collapse here. Anyway, so the thing is that if you do try to collapse all of this data, then it turns out that in the vicinity of the transition, it looks like there's a scaling collapse of the form W by L, which once again suggests that as L goes to infinity, your critical disorder strength might go to infinity. Then there are other arguments which have to do with looking at calculating a diffusion constant for this system as a function of the disorder strength. And the argument sort of says that there is a diffusion constant for any value of W which is not equal to infinity. And further, if you try to sort of see how this, from this diffusion argument, how this W would scale with system size, that again, once again you can get a linear scaling, and this suggests that the MBL phase does not exist. But then there are people who have proposed counter arguments saying that, oh, maybe this diffusion argument doesn't really, this form of the diffusion constant doesn't really work for large values of disorder and up to large system sizes, and so maybe this argument fails and you do indeed have MBL. So this is sort of the question now, that is there, so what happens? Do you actually have an MBL phase, in which case you would have this kind of phase diagram? L is the system size. So in the infinite system limit, you actually do have 2 phases, MBL and ergodic, separated by some critical point. G is the parameter that you're tuning here. It could be, for instance, the inverse of the disorder strength. And this is the system size. And so if you're at finite system size, then you're not down here, you're somewhere here. And so you will see some MBL regime, some ergodic regime, and something in between, which is where you see all these drifts happening. On the other hand, if there is no MBL phase, then this is what the phase diagram would look like. Once again, you would see these regions, but then as you go to larger system sizes, you'll see that you'll only have the ergodic phase and not the MBL phase. Okay, so in the remaining 3 or 4 minutes, let me just tell you one last thing about the story, and then I'll conclude. So in order to settle this, if at all it can be settled, right, it would be nice to have, just like we've had a phenomenological model of the MBL phase, it would be nice if there was a phenomenological model of the MBL transition itself. And of course, many models have been proposed, but it turns out that the most promising one seems to be what's called the avalanche scenario. And here the idea is the following, that if you have a sufficiently large disordered system, there will be regions in that disordered system in which the level of disorder will be low just by random chance. And so those are locally going to look like thermal regions, and they are going to be adjacent to regions in which the disorder level is high, which would look localized. And so the question is that if you assume that these were not talking to each other, of course they do talk to each other because there's a hopping. If they don't talk to each other, then they're stable by themselves. Now when you introduce the hopping, is it possible that the thermal region swallows up the localized region and just keeps doing this so that the whole system becomes thermal? Or is it that it starts swallowing up the localized region and stops at some point, in which case, of course, then the system doesn't completely thermalize and it remains localized with these local thermal regions, and this is called the avalanche mechanism. And it turns out that there is a way in which you can actually make this argument mathematical, and there's a certain condition in terms of the local integrals of motion that you can postulate, which would tell you which would happen. Whether the system would thermalize, the avalanche would continue, swallow up the whole system, or whether it would stop and you would actually have an MBL system with these local thermal regions. And it turns out that that has to do with the size of these local integrals of motion, which in turn depends on the disorder strength. So this gives you a certain criterion for when the transition happens. It turns out that from this you can also get a scaling which actually does satisfy the bound that I had told you about, and there are certain issues that have to do with the dynamics of this process. But long story short, and this is I think my penultimate slide, so you can now take this mechanism and you can see how this applies to a microscopic model like the standard model of MBL. What does this have to say about the standard model of MBL? And so that was done in this paper, and it was found that the avalanche mechanism, right, if it is operative, is something which would actually give you an MBL phase only for values of disorder which are significantly larger than thought before. So I told you earlier that the value of disorder in the standard model for which you have the transition is at 3.5. It turns out that with this mechanism, it's actually closer to about 20, about a factor of 5 or 6 more. And the point, of course, is that in finite size numerics, you don't ever nucleate these local thermal regions because you don't have a large enough system size. So you don't really see this avalanche effect unless you somehow artificially put it in by hand, even in the numerics. But then it turns out that there are other effects, which I don't have the time to go into, which can kick in the absence of this avalanche mechanism, which could actually give you something which looks like the MBL transition for a finite size system at about the right values of what you see in numerics, at about 3.5 or so. But as far as the avalanche mechanism is concerned, there's at least a lower bound, and this is not like a fixed number, this is a lower bound, that the value of disorder at which this transition takes place is at least 20, and it could be higher. And so this doesn't really settle the issue of whether in the thermodynamic limit you actually, this critical value of disorder due to the avalanche mechanism is infinite or whether it's finite. And so this is my final slide, my summary. So basically, as far as MBL is concerned, and you're confining yourself to numerics on systems that are accessible numerically and also experiments over the time scales that are practical, there seems to be evidence for strong non-ergodicity in the numerics, right? And the non-ergodicity is indicative perhaps of an MBL regime and not an MBL phase, that within that time scale and within that length scale, you see strongly non-ergodic behavior, and that's a regime. And you can enter this regime from a thermal regime through some kind of crossover. But whether this regime is actually a phase, whether it continues to exist up to the thermodynamic limit, is something which is still not clear. The jury is still out on that, right? And whether MBL actually exists will depend on the answer to this question as a proper thermodynamic phase. But if it is established to exist, then it will perhaps be the only known robustly, and robust is important here, non-ergodic phase. And so that is, of course, very, very important. So thank you very much. And sorry for going over time a little bit.
Thank you, Subrata, for giving such a wonderful overview of non-ergodicity, decoherence effects in an approach which is different from open quantum system approach where you explicitly bring in the effect of an external heat bar. The talk is now open to questions, comments, etc. Yes, sir.
Yeah, could you speak into the mic, please? Yeah.
Sir, thanks a lot for the talk. Sir, I had a question about the nature of the eigenstates of a thermalizing Hamiltonian being thermal. I asked this because, like the standard model, another common way to look at thermalizing dynamics is via random quantum circuits.
You could get what?
Another way to look at thermalizing dynamics is via using random quantum circuits.
Oh, right.
And in that case, I know that entanglement and all measures are there to classify the thermal nature of a state, but intuitively it seems very different that a random quantum circuit's eigenstate and an eigenstate of a simple Hamiltonian model are still similar in...
Yeah, so you're asking intuitively, it seems strange that what you get from a random quantum circuit is similar to what you would get from a model with a well-defined Hamiltonian. Okay, so you can... All right, so I was talking about conservation laws and conserved quantities, right? And so the thing is that if you have a Hamiltonian model, even if nothing else is conserved, the total energy is conserved just by construction, right? And so the thing is that anytime you have a conserved quantity, then in some sense the existence of the conservation law itself slows down the dynamics to some extent, right? Now, when you have a random circuit model, right, when you have random unitaries which give you the evolution, then you don't even have this conservation of energy. So all that's happening is, in some sense, that when you're looking at a random circuit model, the one conserved quantity, which might have been slowing down your dynamics slightly, is also got rid of, right? And so something similar, for instance, happens in flow case systems, in which it's not a random evolution, but it's a periodic evolution, but again, the energy is not conserved.
Hello, sir.
There are questions from section.
Yeah.
So I have two questions, very small. So one is, you were saying that in many body non-interacting case, the states can be localized if they are localized in single particle eigenstates. So does it mean that whatever eigenstate nature is there in single particle, it will be exactly same in many particle in non-interacting case?
Is it the same as the many particle in the non-interacting? Are you saying, so are you asking if the localized single particle states are like the many body states in the interacting case? Is that what you're asking, or something?
Yeah, localized or delocalized or multifractal, whatever is there in single particle, will it be same as...
Okay, so this is the thing which, so this thing seems to have turned off again. I went over rather quickly. So the idea here is this. So imagine that you have single particle states, and you also have this one particle in your system, right? So then, and you're looking at the eigenstates of the system. So this one particle could then be in any one of these single particle localized states. Now imagine that you have a non-interacting system, right, in which the single particle states are localized, but you have many particles in the system. And let's say these particles are fermions. So now you're populating these states by filling them with fermions. And so you can ask, well, what does that look like? So there what you have to do is you basically have to specify the occupancies of each of these single particle states. Is the state occupied by a fermion, or is it not? And so this is the notion of the many body state with all single particle states localized, right? And you're describing the state in terms of these occupancies in what's called Fock space, rather than in the single particle state, where you're just talking about the wave functions of the individual states. So that is how you sort of go between the two of them. And of course, if you wanted to write these Fock states in terms of the single particle states, they would be Slater determinants of the occupied single particle states. So that's how you relate them. And then when you turn on interactions, of course, the question is, these interactions will give you tunneling between these many body, single particle many body states. And then do they also continue to be, do the many body states, even in the presence of this tunneling, continue to be localized in some sense, or do they not? And that's the whole question of NPL.
Well, with due apology, we have to wrap up the session as I've been instructed by the main organizers. But Subrata is around.
Yeah.
Over tea, you can ask him more detailed questions. And let's thank him for a wonderful presentation.
Thanks.